In this video, I'm just going to talk through a solution I really like for what at first seems like an impossibly difficult problem. Here's the problem. Imagine randomly generating a number between 0 and 1. Then, add this number to a total, which will start at 0. Now, we repeat this, continuing to add to the total. The question is, how long on average will it take for this total to exceed 1? If you look online, you'll find plenty of solutions that use tricky calculus or indecipherable symbols. But as a student myself, I think this method is a really neat demonstration that complicated conclusions can be drawn from simple, intuitive methods. There are a couple of things you need to know to be able to understand everything in this video. I've left links to explain this for them in the description below. Volume formulae and scale factors, basic concept of what an integral is, expected value calculation, manipulating factorials, and finally e and the exponential function. The first step to any problem is to make it easier and break it down in order to understand what's going on. So let's start by considering how likely we are to have exceeded 1 at a discrete number of tries, as that should be easy to work out. So, after one try, the chance is 0, since the total cannot exceed 1, since the maximum for this number is 1. After 2 tries, we can consider the first try as a number x, and the second try as giving a number y. This gives a square region of possible points after 2 tries. However, we also need to condition on whether they add up to 1 or not, which we can do by adding the line x plus y equals 1. In this case, it's easy to see that the chance of them exceeding 1 is a half, as the line cuts this square into 2 identical triangles. Now, we can extend this to the third try. Here, the set of possible outcomes can be represented by all of the points inside this unit cube. However, we then have to cut this cube through the plane x plus y plus z equals 1. We can visualize this by considering that this plane is going to pass through the points 1, 0, 0, 0, 1, 0, 0, 0, 1, all these 3 edges of the cube. The resulting shapes are therefore this tetrahedron and the other shape, which is the rest of the cube. The tetrahedron is much easier to think about since we actually have a volume formula for it. The formula for the volume of a tetrahedron is a third times the base area times the height from that base of the apex. Let's consider the intersection of the plane and the cube as the base. Since we know that when we set one of the values to 0, the feasible region is just our 2D representation from before, each of the side lengths of this base triangle is going to be root 2, as it's the diagonal of our original square from before. Using half AB sine C on this equilateral triangle, we can get an area of root 3 over 2 for the base. As for the height, we want to use this right triangle. We already know the hypotenuse is 1, as is the side length of the unit cube. And as for the bottom, we can cut the base of that equilateral triangle like this to easily see that that length is root 6 over 3. Then we can use Pythagoras on this triangle to work out that the height is going to be root 3 over 3. And subbing all of that into the formula, we get that the total volume is 1/6. Interpreting that in the context of the problem, that means that the probability that the total has not exceeded 1 after 3 tries is 1/6. Alright, so this representation is pretty useful for considering 2 and 3 iterations, but it becomes really hard to use it to understand 4 or more, since we can't, of course, visualize 4 dimensions. What we really want to do here is come up with some kind of rule for generalizing the volume, per se, of this n-dimensional shape. To get that, let's look at what we know so far. Well, we know that the one-dimensional version of this thing looks like this, and it's just a line. We know that the two-dimensional representation is this triangle, and it has area a half, and in 3 dimensions, it's a tetrahedron here with area a 6th. You may already start to see a pattern emerging, but let's investigate further. Starting at our one-dimensional shape, how do we actually get a 2D shape? Well, we add an extra input, which maybe we call y, since it goes along the y-axis in this representation, and y is somewhere from 0 to 1. When y is at 0, we just have the same line because y hasn't contributed at all to our total. But as y increases, the constraints on the other number, x, gradually change, and when y is at 1, the other number has to be 0. Essentially, this can look like stacking a load of lines that gradually get smaller, building our triangle. At this point, you might start to recognize this as an integral. But let's look at the other one we can visualize, going from the two-dimensional one to the three-dimensional one. Again, we're introducing a new number, which maybe is z, since we're considering the z-axis now. When it's 0, we get the same thing as before, as it hasn't contributed to the total. That's just the right triangle from 2 dimensions. As our number gets bigger and bigger, we essentially get new right triangles, where instead of the area being defined by x plus y equals 1, it's instead defined by x plus y equals some constant c, where c is 1 minus z. Once again, we're adding up this set of continuous areas, which again looks like an integral. So how can we generalize this? Well, we can imagine that we have our shape in n dimensions, with a volume of big N. We introduce one more number to make this our shape in n plus 1 dimensions. Let's call this capital L for length. When L is 0, we start with the same shape as in n dimensions, so that has volume n. How does this volume change then as we increase the new number up to 1? Well, we know the resulting shapes will be similar to the original shape with volume n, but now the side lengths will have 1 minus L instead of 1. So, the ratio of the lengths between shape at L equals 0 and L equals a new value is going to be 1 minus L over 1, which is just 1 minus L. And hence, the ratio of the volumes is going to be 1 minus L to the power of n. Since we know that the starting volume at 0 is n, this means that at any given value of L, to work out the volume of the slice at that point, we need to do n times 1 minus L to the power of n. What we need to work out is the infinite sum of all of these small slices between L equals 0 and L equals 1. So what that means is we want a definite integral from 0 to 1 of capital N times 1 minus L to the power of small n with respect to L. The antiderivative of this expression is going to be negative n 1 minus L to the n plus 1 all over n plus 1 plus c. Evaluating this at 1 will just give us 0, as 1 minus 1 equals 0 and 0 to the power of n plus 1 is still just 0. While evaluating it at 0 will give us negative n over n plus 1. And so the definite integral here is n times 1 over n plus 1. This is quite neat actually, because it's telling us to get from an n-dimensional version of the shape to an n plus 1 dimensional version, we just need to multiply by 1 over n plus 1 to the original area of that n-dimensional shape. So, when we start with our two-dimensional version, that has area 1/2, we just need to multiply that by 1 over 2 plus 1, that's 1/3, to get the volume of the 3D version, and that works. A half times a third is a sixth, and that's what we worked out as the volume of that tetrahedron. To get the volume of an n-dimensional version of the shape, what we're doing is 1 over 1/2 times 1/3 times 1/4 times 1/5, etc., up until 1 over n, which is just 1 over n factorial. Okay, great. How do we actually interpret this in the context of the problem then? Well, it's essentially telling us that at any given number of tries, n, there is a 1 over n factorial that after that nth try, the total has still not exceeded 1. But what we want actually is the chance that it succeeds on precisely that nth attempt. To get this, we need to know the chance that it fails on every try before. That'll just be the chance that it fails every time and the one before, which is just 1 over n minus 1 factorial. But also we want to take out the chance of it failing every try before and that try itself, which is just 1 over n factorial. So the chance that it exceeds on the nth try is going to be 1 over n minus 1 factorial minus 1 over n factorial. To find the expected value, what we need to do is we need to sum every outcome multiplied by its probability. For the nth try, the outcome multiplied by its probability is just going to be n over n minus 1 factorial minus n over n factorial. To get the same denominator, we can divide the one on the right by a common factor of n to give us n over n minus 1 factorial minus 1 over n minus 1 factorial, which is of course just n minus 1 over n minus 1 factorial. Dividing this through by the obvious common term of n minus 1, we get 1 over n minus 2 factorial. Now, we don't need to consider n equals 1, since the chance at n equals 1 is just 0. So the minimum value of n minus 2 is 0, and then it just increases by 1 each time, infinitely. In other words, we have a series that looks like 1 over 0 factorial, plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, etc. And that is just E.